So yeah, Mark, furthest we've gotten with adjusting robots, we've managed to make them kill themselves by slapping their own shields.
Oh yeah, go get them.
Which means there are shoes.
They're like weird bargain, not weird.
All right. So, is this reading? This is reading. Good. Good, good, good. All right. Test, test, test. Looks pretty good. Looks pretty good. I think sound should be coming out right now.
All right, I'm going to test it.
All right. Yeah, you can hear me. Great. That sounds really good, actually. Cool.
All right, my computer.
All right, hey everybody on the live stream. This is Mark. We're going to be starting up in just a few minutes. So hang tight. You're in the right place. We're doing the right thing. And I'll be with everybody soon. Okay. Hi. Good. Thank you. Helen, how's your talk? Heard you raffled off one of my books.
I tattled.
Yeah, the 15-minute push ended up being well worth it. Do you need power? I could make there be power. If you need power. Lynn.
Why, that would be awesome. I don't want you to trip over it,
It shouldn't be coming out here. I mean, everybody else will trip over it, but. That's just kind of lucky that. Like, I went to media services to get like the video camera and things, and they're like, take cords and power strips and extenders. I'm like, all right, they'll come in handy. Just take it. Farzine, do you want headphones so you can do some sound monitoring for me? Do you have some? That's enough just to make sure that like I'm not killing them, or you could feel, because then you can hear it yourself instead of waiting for complaints. You're gonna do that weird like, oh, one ear is like delayed thing, but every so often, once I set it when we start, I'm not gonna touch it. So just so we can level through there. All right, I'm gonna test. I think this is a good level right here. I think you should be able to hear me loud and clear where I am here. All right. So now I can turn myself on and off. I know where on the knob to go. There was also supposed to be a second channel that was a room mic, but that didn't happen. So nobody else.
I'm talking right now, and I'm gonna see if then I end up hearing myself.
Well, you shouldn't be able to hear anything. The only mic going into the live stream is this. So I'll be repeating questions, and well, it's also off right now. So.
Right, no, but I just heard myself, and yes, I can hear myself a little bit, but yes.
Okay. Okay. I mean, if there's any problem, like, we'll fix it. Hey.
We'll go for like 40 minutes, is that about?
Yeah. Yeah.
And then
I had it. The slideshow ended up bigger than I was hoping for in slide count, but a lot of them are like intermediary transition slides. So I was aiming for 40 or under. So I'll call it in the air as we go too, like what actually requires detail and what doesn't. There's some stuff in there that's left over from the proposal that's like, here's what the activities look like. It's like, we don't actually care anymore. Let's get to the abstract stuff. I do have the new bit in there.
you have Ashley's work in the presentation?
Yes.
Good.
Yes. Yeah. Hey. Yeah, that is in there. I should have. The organization of it ended up completely different than the document, which I like.
Oh, that's good. Well,
Yeah.
then one can influence the other.
Well, because it's done in that the three pillars.
Oh, great. Oh, good. Well, that. Yeah, I guess it's easier to do in this than
It's an easier way to talk about it. It's not the right way to write about it. Because it's well the like setup and methodology like intertwines a little bit
yeah.
as we go. I sort of did it to tell the story better.
One of the comments we see when we go over the written document is that pretty much each and every chapter needs a map of the chapter presented up front.
Yes, I agree.
Um,
I recognize that like the day after I sent it, I was like, oh, I didn't do the organizational
so
stuff at all.
maybe in a way it's an asset that you didn't, because this three pillars thing could be part, like that would be an upfront thing. Here's the
Right, and how I
when you go to each existing chapter, which still makes sense, you can say
Okay.
this is mostly pillar 2.
oh, so I can contextualize
Yeah.
it, and that can help build that structure that I'm missing.
Yeah. Right.
Okay,
So then
that's
you
a good
get
idea.
both, really.
Okay.
Yeah.
Well, because that's like exactly what I expected to be missing is stuff like that.
Yeah, no, you have to like get a whole thing out before you can see how to reassemble it.
Yeah, this as always, like I kind of like in building this putzed around until I found like kind of the design language that would be the way to do the whole thing.
Yeah.
And the three pillars, I found a way to do it with that.
That's great.
And so I think it's gonna be good. It's gonna
Yeah, I
be
liked your graphic with your Facebook invitation.
My cheesy Facebook graphic
No, visuals are good.
now with live stream.
Well, yeah, I noticed that too. Hi, Mr. Sherman. Congratulations.
Hey, hang on. We got like an hour. Well, he could walk in late. All right, everybody on the live stream, thanks again for joining us. We will be starting up in just another minute or two. I'm just gonna check if that's still recording. It should be. Hey, check my angles here. Yeah, still looks good. Hey, Drew, welcome. Yeah, we can start.
30 seconds. All right. Thanks everyone for coming. This is a fabulous turnout. It's a part of Mark, I imagine most of you know. Oh, and there's
Only
a
mic I have
microphone.
on the live stream.
Okay. Right, for coming. Thanks for those who are watching on the live stream, or watch afterwards on the recorded stream. So, so the format today is Mark is going to present his work. It'll be about 40 minutes. Then we'll allow the committee to ask the opening round of questions, public, and after that, the whole audience will be able to interrogate and help Mark understand the work, and we'll all make sense of it. This is a collaborative process, really. And then after that, we kick all you guys out, myself and the committee. Who I should introduce? This is my colleague Jay McCarthy at UMass Lowell, and Franklin Turback from Wellesley College, who have already both Jay and Lynn have made substantial contributions to the project with Mark already. Thank you guys for doing that. So after the public questioning, everyone gets ejected, and the three of us talk with Mark, and then after that we eject Mark, and the three of us confer. And after that we give the decision. And then we grab Mark for some more time to explain, basically how we have to wrap up. Okay, Mark, take it away.
All right. Thank you. Thank you everybody for coming today. Great. All right, so there is a lot to do, so I'm going to dispense with my normal pleasantries and jump right in. We are detecting student progress during programming activities by analyzing edit operations on their blocks programs. But of course, we need to break that down a little bit. So starting from the bottom going up, blocks-based programs. So I'm working with MIT App Inventor, blocks-based programming, where the atoms that you edit are blocks. They snap together. There are still open fields like text. You can name functions. You can type in text literals and numbers. So there is still some typing in there. But the core item is stuff that drags and drops and pops together. Gives us a nice atomicity to work with. And what we're going to be looking at are those edit operations provided by the atomicity of the blocks. And what we're doing with those edit operations is we're looking at kids doing programming activities. Specifically, these are middle school students, 6th, 7th, and 8th grade, who are novices. They're in their first computer science course ever. And course is sometimes a liberal term. Sometimes we just got them for summer camp, or maybe they've had a class or two. So they are largely amateurs, and they are 10, 11, 12 years old. And what we're looking for is how they progress during that activity. We're not looking over the course of a semester or a course. We are looking within that lab session itself, that 30 to 40 minutes, trying to get updates on how they're doing right now while they're working. That's a big piece, and that's what frames the whole thing. So this is a dissertation in 3 acts. First, we have fine-grained capture of that data of the students working. Every change they make, we use the term fine grain to describe that we are looking inside the program as they program it, rather than just looking at the final piece they pass in at the end, which is traditionally how classes work. You pass in a final product, and that's what you get evaluated on. So fine grain is that tighter data of each edit operation, each change. I'm going to present to you a post hoc analysis method that I made that helps us extract whether they are progressing or whether they are flailing. This was done post hoc style in that I collected the data and then sat down with that data and devised an algorithm that finds the feature I want to find. And we'll talk about that. And then we use this middle thing to create a classroom dashboard, a teacher tool. The end goal of this is to create a tool for teachers to help them work better in that lab session while the class is going on. Everything good, Farzine? Thumbs up? All right. Farzine is watching the live stream, so if you're on the live stream and you have questions, you can type them into the chat. And Farzine is watching that chat to relay them up to me when the time is right. So you will not be forgotten. So the 3 acts more so look like this. One leads into the next into the classroom dashboard. And there are pieces of each that we are going to talk about. These are the 3 major chapters of the talk that we will go through. So we will see all of these in turn. So starting with Act 1. We are going to talk about, as quickly as I can, honestly, to fit this in 40 minutes, the actual code snapshot system. So every time the student made a change to their program, we captured the state of their program. Simple as that. So here is some App Inventor, if you've never seen it before in your life. Visual interface for designing your app. This is in a browser running. You can drag some stuff in, change properties of the components that you've dragged in that you can see down here. And those properties are just updated, and the app will launch with that. And here's the good stuff. When you switch, I'm going to drag a text-to-speech in first. And here are the blocks. And watch as I program at blinding speed. So the blocks are in menus, so you can recruit a particular block to serve the function you want. I'm going to do it 2 different ways. I'm going to pull that in, and you see the snapping action come together. Every one of those snaps was a change. Also a change of interest that gets snapped are anytime you change one of the properties out here in the designer. Those were also changes that were captured. We ended up not looking at that in this. That data is there for future work and evaluation that can be done. But back in the blocks, we're doing some more changes. And every single one of these changes, every move, even if it doesn't change the app programmatically, you just move the block in space. You did something. And that's important because we're trying to look at whether a kid is progressing or whether they're lost, whether they're stumped, whether they've given up. And moving just blocks around in space or blocks that aren't connected and aren't helping are very important to that. So it captures everything every time. And a little more formally, here's what happens when that change occurs. Every change, every one of those blocks that moved triggers a capture. It grabs that designer, which was that drag and drop UI, where I put a button and the text stuff in. It grabs the entire block editor, including commented out code that isn't attached to anything. And it grabs metadata, the username, the project name, and the time. So it also has the time that it happened. And where does that go? Well, it goes through the internet to my receiver server at the other end, which looks something like this. This is the part where it got, we had to be very careful because we are dealing with human subjects research. So everything has to be IRB certified. And so the first step is to de-identify. We de-identify by replacing their real username with an automatically generated code name, which had to be kept in a database so that the same person would always get the same code name. But that had to be kept separate from the rest of the data store so you never knew what code name belonged to what real person. And that is what we had to do to make this IRB approved. If you want some more detail, it looks something like that. That's the original whiteboard from a year and a half ago. Anyway, so the activities we had the students do, I'm going to take another step forward. That's how I capture the data. Let's talk about what the students were actually doing. This is another part I'm going to turbo through, especially if you saw my proposal. This is the same stuff. So I didn't invent a new activity and rerun a study in those months. So we have two activities, the debugging activity and the temperature activity. They differ in complexity. They differ in skills needed to achieve them. The debugging activity in general was very well scaffolded. It was based on an assignment most students had already done. And the temperature activity was very poorly scaffolded. It used a lot of new concepts that they were seeing for the first time. And that kind of gives us a variety of stuff. Same basic cohorts, but there were far fewer who did the temperature activity because this one wasn't run in schools. That's just a little detail why this one has a lower N than this one does when we get in there. The debugging activity I ran for like a year and a half. So we have like lots of classrooms, both formally in classroom time and informally in summer camp. So here's what they look like. Turns out at this stage of abstraction that we're dealing with today, this is less important. I can just tell you that the debugging activity has 3 levels of goal in it. It has 3 little sub-goals. It has 3 bugs in it. That's why it's called the debugging activity. I gave them a broken app, an app they had already seen, and asked them to fix it. And if they do it right, it ends up working correctly. That's all you really need right now. And the temperature activity was a temperature converter where the user would put in degrees Fahrenheit and it would give you the degrees Celsius. The trick to this one was their goal was to implement this equation, this Fahrenheit Celsius expression. So that was what made that tricky, was both there was arithmetic involved. I gave them the equation. I gave them the transference equation. But they had to figure out how to express that to App Inventor with the setup I gave them. So that actually put a lot on them, as we'll see. Well, actually, it's fine. So very, very brief synopsis of the methodology. Students do the activities, whether in their classroom or in their summer camp. Either way, it was a 30 to 40-minute experience for each student. They did these activities on a special instance of App Inventor in which I had my instrumentation running. So we collected the snapshots on every single change they made for every kid. And I was all neatly organized and de-identified and code-named. And then we looked at it later. The rest of this talk is this 3rd bullet. And let's see, how do we look at things later? This is a feature that didn't quite exist yet at the proposal, so I'm really excited to show that we can play back this. Remember, we captured time. So you can know how long each block took. This is not quite real time, but it is showing you as a real student doing the debugging activity, showing the moving blocks around and trying things. And I am manually knocking it through next frame, next frame, next frame, but it shows every single change they did. What you may notice is you might notice some strings. So they're dragging out some string literals here, and the text is magically appearing. You're not seeing them type. That's because this is post-filtering. I already went through and have a little algorithm that goes, and when you're typing in a string, it gets rid of all the changes that are the individual characters and just gives you the end string. Because character by character editing for learning analytics has not been terribly useful, and that is an actual literature quote that I have. So this is the level of abstraction we want. That's why text just appears. The kids weren't magic brain typers. So anyway, that's what it kind of looks like in playback. This is a real kid. I don't know who, but this is a real kid's data who really was trying to solve this problem in a classroom or in a summer camp. And this is the first way we have to analyze the data that comes in, is just walking through these, playing back, and seeing what you see. So a quick word on participants. I already said most of this. I had 86 in classroom. I had 41 in summer camp. There was some slight overlap. Some kids were in both. if they use the same account, then they would be the same person. Hard to tell. For 127 individual people. Some students did both activities, so 127 people rendered 129 total activity instances. All right, so now we're going to talk about the first level of assessment, which is manual assessment that went through looking at those blocks. So looking at the blocks playback, actually going through all 129 activities, and I have to give huge credit to Ashley, who's here. She was the research assistant who actually slogged through all this data and did all this coding. And it took her a solid week to do it. And what it reduced down to is, was the student good or great? Now, this is just looking at their blocks. It's actually the same thing they saw. We don't know what they're thinking, but we got to see what they see. Were they flailing, disengaged, or otherwise lacking traction? Were they moving the same block in and out forever? Were they just typing jokes into text strings because that's fun? That actually is that's actually a sub-finding. That's a huge indicator of being off task, is just typing random stuff into text strings. Like at some point, it's going to flash by on the screen. There was the entirety of Twinkle, Twinkle, Little Star in a single text literal. And that's exactly the kind of behavior we're trying to find. Because to a teacher who's standing over here and you all are working on your laptops, it looks exactly the same whether you are actively engaged with a problem or typing in Twinkle, Twinkle, Little Star because you have no idea what's going on. So anyway, that's the mission we're on, and that shows you how important it actually is. And most of them were coded as none of these. That there was nothing particularly, they were fine. They weren't awesome, they weren't terrible, they seemed fine. That's how this coding ended up. And very few of them actually had both, which are kind of cool. And I have a whole section on that in the manuscript, where the person fought really hard, but then they seemed to win at fighting. So that's a whole other area that we'll get into later. Yeah, that's enough for now. We'll come back to this in a little bit. So having done the first pass through the data using playback, we're now ready to start not real analysis, but trying to do automatic feature extraction, trying to design our measures to do the analytics that we want to do to be able to generate that measure of, is this student in need of help right now? That's always the end goal. So the data import process, this is less important now. If you want to nerd out about this later, I think that'll be the right thing. Pulls it out of the database, filters, does stuff, and then ends up giving you a project that you can work on. It's a lot of fun if you want to look at that later. What can we detect? So there are two types of feature extractor that I did. This is the first type, which is, I called this forward design, where I started with the data and said, what can I pull out of this data? And I can detect what kind of change it is. Did the block move in space? They just moved around on the workshop. Was there an abstract syntax tree change? Did it change the functionality of the app? Did the code actually change? Because you can move blocks around that don't actually do anything. Where they are in the workspace has no bearing on the execution of the app. But sometimes it does. Was it a text field change? Was a block added or deleted? Was some other property, like on that front panel, changed? So those are the forward direction. And we spent a lot of time playing with these and seeing what patterns we could draw out of this. But then we have to remember, what is it that we want to do? We want to detect this concept of flailing. And what does that really mean? We're really trying to help teachers. And it's not just we want to know when they're flailing, we want to know progress versus flailing. And I am asserting that they are sort of a zero-sum thing. And there is a neutral in the middle, but if you're not one, you're probably doing the other. And the same tool should easily be able to detect both. The reason we want it is because we want to know what their progress is. Are they progressing? Are they flailing at any given moment during that activity? Real time, live, right now. So we need it to be fairly simple because this is something teachers are going to glance at and then run off and pick a kid to go work with. So this isn't something that can take a month to process, and it isn't something that takes a PhD to interpret. So how do we do this? And here's where there was a big pivot from that forward design of extract, 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 into we already know where we want to use this tool that doesn't exist yet. Where do they closely monitor each and every student to make sure they're on track, and where are they most likely to lose them off that track at the beginning of the course, the first half? Are these activities open-ended? They're not. The first half of the course is very on rails, and having seen App Inventor courses around the world, I teach teachers how to teach them. I know the curricula that are in place, and these activities all have canonical solutions where we know basically what the answer should look like. There's variation. There are different ways to get at that functionality, but we know what the answers basically should be in these. So I'm constraining our problem of the flailing detector to these on-rails problems where we know the question, we know the answer, we know what the student is trying to do, both because that makes the rest of this thesis possible and is actually the useful tool that we need. And that brings us to the reverse designed analytics. So the first one was starting from the data moving forward, and now I'm starting from the goal moving backwards into the data, and that's how we end up with this, and this is where things get exciting. So the solution particle method is a way of, and there are other things that are similar to this in the world. The concept of this is not entirely novel. It's been adapted. A solution, the right answer to one of these apps, is composed of many blocks. You've already seen some. Lots of these little blocks, and those blocks make great atoms. And we already have that word, atoms. Any relevant block can be part of a solution. So if you have that 5/9 thing, that 5 anywhere on the workspace counts for something, because maybe that will get pulled in to be part of the right answer in a little bit. So it searches for blocks that might be part of the answer, and then searches for structure, whether how close to the right answer those blocks then are when put together. And it's called particle because we have a nice little metaphor here. We have the atom, right? And we can put them together and we can make things. We can put different atoms of blocks. That's a division block and a number block. And then we can put a whole bunch of them together. We can make these big complex molecules. And a molecule ends up being a solution. So we call it the particle analysis method. And by we, it's literally Fred and I at this point. So if you all want to catch on with that and make that a thing, we'll see. And I'll give you a paper to cite in a couple months. So that's the basic concept, is if you want to know how close they are to this, looking for that doesn't really help. Also, it might be a little different. They could rearrange this a few different ways and make this work. The multiplier is transitive. But if you're looking for each individual peach, and this is a point, and then you get another point for it being in its correct parent, and then that thing has a point for existing, and that has a point for being in a parent in the right place, then eventually you can score all these up and have a pretty good indication of where that student is. I skipped a little too far back. Come on, buddy. There we go. So there are two kinds of tests that make up a particle. There's the find, which just finds a block. And then there's the inna tests, which take that block and say, are you in the right thing? Are you in your correct parent of where you should live? And top-level blocks don't have innas, and that's fine. We can do, so the find basically generates a list of candidates. So if they have a zillion numbers that are out and they only need one, every single one of those is a candidate, still scores as 1 point, because you have one or more possible matches to that solution fragment, to that little particle. And then you use the innas to reduce that list. And once you get that list to 0, you stop adding points. That's basically the algorithm. Formally, it looks like this, where you have a test that is a find, and then you have innas. My test runner currently goes up to 1 find and 2 location finders. You can keep going, and I have this I can show you later. So you find all the blocks that potentially match. If you find any, then you increment your score, and you go to see, is it in the right position? Do any blocks remain after the position test? Then run another position test if there is one. Sometimes you only roll 1. Sometimes you don't have any, depending on what the block is. This sort of defines the language that you define a solution score. Anyway, what it looks like is this. So here's a student solution score. It's starting not at 0. It's starting at 9 in this activity because I gave them gift code. The project that they opened was not empty. This is incredibly common in any assignment of really any flavor, especially in computer science, I gave them some structure and they had to improve it or they had to debug it. So they start with something, and the further you are up on this axis, the closer you are to the canonical solution as written. And even if you don't nail that solution exactly, I can show you getting closer to it, and that's important. Because even if that student never gets this, if they come up with some other variant that floats in this space somewhere, they started here, and we can see them working their way up towards it. This is actually a really good run. They take a few different shapes. Here are two students put together. Oh, and the horizontal is time, by the way. Forgot to mention that. So here the red student is what we coded and came up with a pattern of smooth that they kind of already seem to know the answer, or they just get it. They blow right through it. It's basically monotonic. This person hiccups a little bit down here right before 400 seconds. And then the one in blue is a second category that we call fits and starts, where they work their way there, but they kind of like, they figure something out, and then they mess with it, and then they kind of break it, and then they fix it again, then they figure something else out, and this is more normal. This is the most common modality as they work through. There's also a third modality, and if you can guess what it is, I bet you can, it's flailing. No significant process, despite trying really hard. Or so this seems, because every one of these notches on the line is a change. A flat line without any block in the middle, without any square in the middle, that's just time spent doing nothing, that's idle. But when you see a bunch of these notches in a row and no vertical change, that person's doing something but not progressing. Sometimes they're regressing, but this one's most concerning where they're not doing anything at all for long spans of time. This is over 40 minutes. And that's as far as they got. They actually got a little better and then broke it and never got it back. So I got to do storytelling later. I have a time for that. So with that, we can now define this word that I've been using without actually putting a definition down. So flailing, in this context, is a period of time where changes are made to the project, but the score didn't improve. So that flat line, where they're doing stuff and doing stuff and doing stuff, but they're not any closer to the answer than they were before. That's our definition of flailing, made possible by the solution fragments analysis, particle fragments, solution particles. That's the name we agreed on, yeah, because it has that nice metaphor to it. So there, we have a definition. More on that. Yeah. Now I get to tell stories. So this, in this form already, gives you a very expressive sort of piece of data that you can interpret. And if you like telling stories, you can start to think you know things about these students. This is a smooth student. This person had big gaps of time, but when they sat back down at their machine, they progressed quickly and steadily. So, you know, there's a big time gap here. This really should be more drawn kind of like, you know, an elbow rather than a line. But they're off to the races. So you say, all right, Mark, but what did they really do? Well, let's go back to the replay. Let's see what they really did. Is our thing capturing what we think we did? So this student is trucking right along, and it looks just like how I did it at the beginning of this talk. They nailed it. That wasn't playing around. They knew every next move, so they did very well. Were they watching someone over their shoulder and copying them? Maybe. But either way, we know that they progressed steadily and evenly. There was even at the very beginning, there's a little dip in there. There's a little dip right here. They drop below the starting code. Let's watch for it. Bam, he pulled that out of context and then put it back in. So here's another one. This one, we saw this chart before. Yaroslavl cattle, that's a code name. Don't know who that really is. They're all cities and then animals, because that gave me a huge solution space, and I knew I wouldn't run out of names. That's all I was so worried about, that breaking while the classroom was happening. Anyway, so what did they really do? Now this is over 40 minutes, almost the same time as the last person, but the last person took a lot of breaks. This person was basically at it solid all the way through. And what we'll see as this evolves is they get up to that first answer pretty quickly. This was in their wheelhouse. that changing this to stop shaking me, that was the easiest bug of the 3 that they had to fix. And they had that. And then they stayed there the rest of the way. They couldn't quite get the next thing. There's Twinkle Twinkle. They couldn't quite grasp what the next thing was going to do. They either didn't understand the problem or they were missing some critical piece to get at it. Whatever it was, this is ripe for needs a teacher intervention. That was the hide keyboard block. That has nothing to do with anything that's happening here. I'm glad I picked this one now. Oh yeah, this kid clearly needed help and we failed them. Yeah, I just had to pick one that didn't have swears. Yeah, Ashley knows. She saw the whole untempered schism of students entering things. Anyway, so they just kind of futz around here, and they're hovering around that same score level because this they kept. They knew this worked. We can deduce that pretty well from this data, both looking at their chart and looking at the blocks. The story we told ourselves looking at the chart seems to be holding up now that we're looking at their blocks. But that's just us looking at it and telling ourselves stories, and it seems to work. So I did a little experiment of, does the particle analysis actually help us isolate that progress versus flailing metric that Ashley so dutifully identified from a week of her life looking at the playback data? So we're going to call the playback data raw in this moment because you have everything. You have their entire workspace flowing in front of you. And then we have the particle scores, which was just that line graph. That's it. So a human coded this, the snapshot playback, and a human coded the particle scores, just looking at their graphs without looking at each other. So Ashley did these, I did these, and so let's see if they compare because so this is smooth, fits and starts, and flailing were the categories that ended up over here, and they conceptually line up, give or take, with good or great, neutral, and flail from that first investigation. And so let's do a little chi-squared, where if the null hypothesis is true, that means they are independent, they are not related. The raw does not relate to the process, but that was firmly rejected when I ran them against each other. So I have reason to believe that the two are related, that the interpretation of the scores, just looking at the line graph, not knowing who that is or when that was, is enough to deduce the same conclusion that you could spend a week of your life pawing through all the raw data of watching the blocks playback. Also, me coding the particle scores took about an hour, maybe 2. Took Ashley 5 days of full-time work to do the same thing out of the raw scores doing playback. So right there, we have evidence towards efficacy in what we're trying to achieve. And that brings us into Act 3, our classroom dashboard. And this is the tool that we're trying to culminate with. So we want to make a tool for teachers to be able to, at a glance, look at this thing and see their whole classroom. A teacher that we talked with later called it landscape view, and I love that word. And I took that word, and it's my word now. And the whole point of it is what we call classroom orchestration. That's what we're looking to aid. And this, there's a lot of good reading on this if you want to talk to me about some resources here. It's not about literally conducting an orchestra, though this person is, and that is a middle school orchestra. Those are the age kids I work with, though, not mine. Orchestration, if you go into some, Dillenborg has a lot of good writing where he just sat down and defined this kind of weird concept. And he said it refers to how a teacher manages in real-time multi-layered activities in a multi-constraints context. This is all the other stuff you have to do to make a classroom work. So there's the pedagogy. There's like, I need to teach the lesson in general, and I need to go after everything else to keep everything on the rails. And here is one thing where technology has made life harder. When you have that computer lab, your ability to orchestrate as a teacher or as a lab session leader or as an instructor at any level, if you have students sitting at computers, your ability to gauge what's actually happening in your room is actually reduced. And we are trying to take that same tech and turn it back and make your life easier so they can then be further empowered to make correct decisions and to orchestrate their resources appropriately, time themselves, other instructors, create pair programming, pairings, whatever it is they have to do to get everybody there. It's already harder because of labs, and we're trying to make it easier. So the design goals for this console, now this is based on our particle scores. We want to know how close the student to the solution each student is. We want to know how much time since they last made progress. Imagine this room and one instructor, and you're all busily working away. I can take a glance at my console, and I should know who's basically there, who's still flopping around at the beginning. But I also want to know how long you've been there. One set of eyes. I can't track everybody at the same time. That's something the tool has to help me do. And how much of that time was you trying versus did you like go to the bathroom? Because that matters a lot. There are a lot of assumptions I can't make about classrooms. And again, one set of eyes. I don't know your classroom. Or even inactive would be they stopped using that app on the computer. They're doing something else. Or they're just lurching back with their phone that they think they're hiding, or whatever it is they're doing. It's not something active. I just hit the mic. I'm sorry, everybody on the live stream. Can you still hear me? Everything working? Good? All right, great. So these were the goals that we had, and we worked through, and it looks like this. Here are 3 students. So each student gets their little cell, their unit, and this is their name identifier on the top. I'm going to punch into 1 so we can see. So indicator A is just showing you their name or the student identifier. These are still code names. Sometimes teachers may want to use real names. Sometimes they may not. I don't know, but I'm just saying student identifier. B, this large blue bar is showing that's the score. That's the vertical axis from the charts we saw. And it is scaled to the maximum score for that particular activity that we're looking at. So as that bar goes up, the closer you are to the canonical solution. As long as you are making progress, that's good. Again, you may not land on exactly the right solution. Your bar may never get exactly to the top if you find some other way to go about it, but at least we can tell you're not going down and you're not flopping around on just the starter code. The bars here on the side are kind of designed after LED sound meters on stereos, stuff like that, where as time goes by, if you are idle, or as time goes by where this hasn't moved, this meter starts to work its way up. And right now, this is scored at minutes, and it goes up to 5 minutes, where the darker color is active, and then it becomes this lighter color when they are inactive, when they are away from keyboards. So that's 4 or 5 minutes of they've wandered off or are doing something else. This is now playing live real data in the console. These are real temperature activities from the summer camp. These are real kids who were sitting next to each other doing the activity. And this is 29 of them on one screen. I know projected out like this, it's washing out a little bit on this projector, and I apologize for that. So what you can see at a glance, I had one teacher look at this and go, well, I see 2 students I want to go talk to right now. So you can see this student, the point cheetah, not doing so great, but their timer is also really low. So they're actively working right now, but they're still down here. And now how long has it been? Oh, see, it went up a little bit and the timer went back down. Every time you progress, your timer falls back to 0. Progression is good. That's what this is built around for you to see at a glance. So who spent a long time without progressing? Oh, they just got somewhere. Rostov na Don, I don't know a lot of these cities or animals, is actually trucking along. They've maxed out their meter. They haven't moved in a long time. It's 5 minutes or more. When it maxes out, it stays there until they make a change and it drops back down. So this gives you that landscape view over the class. And I said, well, this is great. It seems to fit what I want to talk about, what I think teachers need, what has been communicated to me through the literature and through experiences and talking to teachers of what could be useful. So let's take it on the road. Let's show some teachers. So I did one-on-one, I say focus groups because that's the right term to tell you sort of what it was like, but it was focus one-on-one at a time. And so I got 2 middle school teachers, 2 middle and high school specialty teachers who only teach technology or something like that. The first 2 middle school teachers were full spectrum middle school teachers. They do a whole class of whatever it is they do, not just specialty of technology. We got some undergraduate instructors, and I had a professor who's in charge of 5 lab sections of CS1 at a South American university. Other people volunteered, but these are the ones who made it in the deadline. Spans a lot of places, US East Coast, clearly well represented, some Midwest, and then we ducked down in South America real quick. So from these focus groups, there were a lot that we can see. I can see right now 2 students I want to go talk to. At a first glance, once you understand and interpret it, it's very fast to interpret. Another thing that was pointed out to me was this was designed to identify flailing students, students that need help. I didn't realize it until I started talking to teachers. It conversely easily points out students who are doing exceptionally well. And if you are in a classroom and have the pedagogy such that you allow for pairing up of those who are strong with those who need some help, this lets you see those pairings. And you can make them on the fly with confidence that they're actually doing this. And it also, there's another class of student that came up a few times with teachers. And this is deeply in the literature of failure modalities, those who ask for help without even trying. So here's your assignment, hand goes up. You can't get away with that because I know you didn't try. Yeah, so in the most common sentence I got was something around, so when can I have it? So overall, they were about it. It is a prototype. It is working on pre-recorded data being played back, pretending it's live. And to be able to take this into the future will take a lot more work, and there's a lot more to be done about logistics and how to actually integrate that. But the concept is very strong from the teacher feedback. So those 3 acts were actually 3 categories of contribution that this work has produced. We have the fine-grained data capture, the snapshot system, which was an evolutionary advance over snapshot systems that exist in the literature and have been used for learning analytics. And that is available now. That is working, that is up and running. You can log into my App Inventor instance right now, and I'll record everything you do. And that's an interesting way to phrase that, Mark. Good job. Analysis method. Our solution particles. This was designed from the goal back into the data and then verified that we have a reasonable above random chance interpretation that this does what I think it does, which is help you understand at a glance if a student is flailing or not. We ran it through the ringer on this pre-recorded data, and I think that's ready to be adapted into real time. And I'm going to make a strong argument in the final manuscript for its computational complexity being sufficiently small that it will be able to be real time when it comes down to it. You saw the flow chart. It's find the thing. Is the thing in another thing? No, move on. That's the complexity of it, but there's a formal write-up that I'm not going to do here. And then the classroom dashboard itself. This is a prototype that I had to get feedback on, so this one's not ready to go right yet. But that's a concept. There are whole piles of future research that can come from this. I'm going to give a very small subset here. The particle scores are just the beginning. They are a means to an end right now for that teacher console. The teacher console needs the particle scores. But what if we take those particle scores and then feed it into some more learning analytics stuff? We collect more people, and we start to use that as a measure for more advanced learning analytics, where we say, could we get to a point where that is a measure that we can use with a model that we've built on open-ended projects, where we don't have to know the answer to know if they are succeeding? And you used to be like, Mark, it was entirely based on the solution. Well, here's how that works. When you know the solution, you watch all that other stuff. Remember all those other metrics? Was it a move in space? Did they change text? There was the forward-pointing feature extractors that we did earlier. Those are still there. And we could use this to teach us how to model those. And I think that is a very, very interesting area to further investigate. So that can turn into models of patterns of those other metrics using the particle scores as a guide, and models of programming skill assessment that can then be useful for the teachers along the way. There are some other ideas, of course. Some particular things to look at, like the students who struggled and then made it, started off flailing and then figured stuff out. There's some more in-depth analytics to look into those cases. The cases of, well, if we do flailing and then they were smooth, well, now we're doing design cycle segmentation, which if you want to know more about that, my poster for my master's is still on the wall right outside, which was all about segmenting design stages in data of students working on actual things. So that kind of thing can be done, and that can be interesting to see how people are processing and how their processes change over time. Over time now meaning months, weeks, years. And that could help watch them go from novice to expert. And these are the doors that are now being opened in front of this work. There's some development we're going to do. Integration of the console itself into a learning management system is no small task. There are a lot of questions that need to be asked, none of which were in scope of this. We just proved that there's a dream of getting that to work, and how that actually integrates with a classroom, and there's data security, there's FERPA stuff, there's a lot of questions to be asked there. And then what happens when teachers say, I love your particle assessment, I love your console, can I put my assignment in it? And I go, ooh, I don't know. So there is some work that can be done, and this is, these are all a simple matter of programming. The previous slide was research. This stuff is engineering. And then optimizing snapshots a little bit. Right now, every snapshot captures the entire workspace. It doesn't have to. It can grab what changed and put them together later. I actually did that anyway in the post-processing and realized, man, if I only grabbed the change, this would have been so much easier for me. But now we know. And so I'd like to acknowledge the National Science Foundation, everybody who helped me program, code, analyze. I had a whole bunch of testers from the system, because again, this thing went up into classrooms and it couldn't go down, because in education research, if you miss your cohort, you don't get another one until next fall. So everybody else, thank you, Fred. Thank you, Jay and Lynn. My parents are here. Hi, Mom and Dad. My wife, Stacy, is here. Thank you so much. Everybody else who came and supported me at any point throughout this, everybody here today watching online, and thank you very much. So I will start by fielding questions from the committee. And for everybody watching online, I will repeat them so you can hear what it is I'm talking about.
So I have some just detailed things I didn't quite understand. So when,
Sure.
when we saw the progress lines,
Mm-hmm.
and we saw like little dips, with little dips like people like moving block out of the socket and then moving something else in.
That's what's like exactly it. There were also lots of big jumps. So this little dip here is that person had a fairly correct answer or a part of an answer, and then they accidentally popped it out of its context. And all of the blocks that were nested in that were also pulled out of that context. So the score did a little dip. And then they immediately saw they were wrong and popped it back in, which is why this went right back where it was. There are also many cases, I believe, if I can find it, this one has it, where there are massive jumps that happen, such as on this red line. Massive jumps, which is they assembled the blocks over here. They pulled out all the blocks they needed. So they all got 1 point for each block existing, and then assembled them, and then dragged the whole thing into final place at once, and then it jumped up. So that's another nuance that is actually detectable from this, is that sort of starts to get into style of programming, which is what I was alluding to in the future work.
Did you ever see any big dips?
Yes. I saw some, I mean, I don't have any up here right now. A dip of this size where it would span 2, 4, 10 is not abnormal. A dip of larger than that, I would say, is very abnormal, especially where, so App Inventor being event-based, all your code is in these little clumps that don't relate to each other. So changing one little clump typically doesn't affect the other little clumps. So giant score swings were not common. It's hard to screw up everything at once in App Inventor. But typically that would be about as big as I'd see in one swing. The swing ups tended to be bigger. The jumps upward. All right, I'm going to focus on the committee, let them sign off on it. Mhm.
and when you looked at the graph, and you use this to decide whether or not your definition was good. And you talked about how you maybe did the P test, right?
Mhm.
One problem that I see with this is that your definition of flailing is that there's a long sequence of changes without an improvement of the score. So you should really be measuring whether that definition correlates with the intuitive explanation as opposed to you being able to look at the graph.
That's
Right?
good.
So what you did is like you basically transformed one data source into another data source that's easier and faster to interpret,
Mhm.
as opposed to like making an algorithm that says this is a good graph. So did I miss that? Is there another step where we look at the graph and we say this person's flailing this instant?
You did not. That is actually a test that I'm overloading the word test. That is an extraction that I have, and I have not put up against that. That is one of the newest pieces that just went in, so I'm glad we get to talk about it. But that is exactly what needs to happen next, and next being before next Friday. Let me get that note down. Should test the definition of flailing.
This particular thing, Mark, where you're just pointing at, Jay, having an algorithm that would look at the time series graph and extract the category from it, right?
Yes.
To make an algorithm for what he looks at.
Right, which is actually where this project first started, was trying to build that algorithm. And then we did all this other work. We then created the particle analysis. And then in swinging back around, I can feed that into that first algorithm I was writing 6 months ago. And I can say I'm pretty confident we're going to get what we want out of it. But until I actually run that, I can only dream. But I'm pretty confident about it. That will be added, and you will be updated swiftly on that.
Can you flip back to your definition of flailing, the one that Jay just,
Because this is incredibly algorithmically detectable. There's no interpretation here. You just set your time window, you set your neighborhood, you set what progress is, and then search.
Let me ask this, and do you have a pointer to this in the future work? Can you only know if it's flailing like after the fact? Like suppose there's a period of time where there's no changes to there's no improvement in particle score, and then there is improvement. Then do you categorize that interval of no improvement as flailing or something else?
So the question is, can we can have this definition of flailing. Can we actually look at it in real time when we don't know the end yet and say, have we been flailing, even though we're slogging along live in real time? And they might be about to improve.
Yeah.
Which sort of asks, what is the window in which you can detect flailing?
Mm-hmm.
And I think that is a parameter that I can throw a little test on to see. In my
But how do you tell the difference between flailing and productive confusion?
Right, okay. So flailing versus productive confusion, that's a note. Because in post hoc, that's really easy to tell. You can tell if they ever got there, such as this one. No.
Okay.
And in this one, they kind of fought with it down here. This starts looking about the same, but then they got their act together and figured something out and worked their way to the top. So in post-analysis, yes, you absolutely can tell. But if we are only, as time swings through here, if we only got, I'm looking at both right now. If we get to time 300 here, both look like they're having a pretty sour time. Red hasn't touched it yet, so you might go, oh, they haven't started. Every single person had a startup time of some kind at the beginning, usually because they would open it and then the teacher would continue giving instruction once they could see it before they would actually start. And that's actually built into the algorithm to ignore already. But as you're plopping along here, if I was just looking at this little segment between 100 and 300 on this blue, yeah, I would say that's a flail. That's a flailing state. And if you have a moving window of a minute or 2 minutes, are they flailing at that minute and how long has it been? I do think that is going to be visible in live data, swinging through from left to right when you don't know the future yet. It will be slightly different than this where I know for sure this person made it versus not. Holly threw her hand up on that one, so I'll take that because that sounds like you're...
So doing this the week for library deadline is not meant to, I'm telling you this because you're going to probably write journal articles about this. This may not hit your thesis, but it should hit journal articles.
Okay.
In our field, we know interactions become much more common now to be using something called Cohen's kappa. When you're looking for intercode reliability, and I think it should be coming out in your work as well.
Mhm.
So Ashley, I'm sure, did an awesome job doing all the coding by herself. But if somebody else wanted to pick up your work and read those coding definitions and try to code something in the same way Ashley did, you need to be doing comparison with somebody else, picking up a segment of what Ashley did with your definitions, and then looking at, do they code the same way? And I think it applies to the work that you're doing too. You're not going to review well for a journal if you don't do that. It's fine. This is fine. Pieces in. But it's work that I can help you with. Dancing and a lot of it lately, and some of it. Happy help you with it. But you're going to need to have that in there because otherwise people aren't going to believe that your definition.
Right. Why should they believe me? Why?
Necessarily great.
Yeah. Why should they believe because I said so?
It's not that Ashley did a good job. The fact is that could somebody else pick up the same definition she was using and code in exactly the same way?
Yeah. Thank you.
Is there any chance of passing the mic around? I'm trying to type the question.
Yeah, I'm trying to repeat on it. Yeah, the original plan called for a second mic, but things happen. Yeah, I'll just do my better to repeat it. So Holly recommended for future work, not necessarily for the dissertation, but for the papers that come out of this, that we need to have inter-rater reliability validated with Cohen's kappa, so we know that the codes that are being extracted from this data set are consistent person to person, that it actually is the rubric as stated that is performing and not just the whims of that person. I think that summarizes it. As you see, I've tangled with that before. Thank you for the pointer. Jay.
One of the things that you mentioned at the end is that turning the prototype into something more production ready is future work, in particular seeing how fast it is. So could you just give us a ballpark about how much compute time it took to generate these graphs?
Yes. So Jay's asking about ballparking compute time to generate the things we've seen relating to the claim for real-timiness in the future. These were running on this very laptop in Python, and the return was human perceivably instant for the entire data set. So I could do these scores and analyze the score at every single time step for every single person for all the projects I have, and my eyes couldn't catch it. So that's why I say I feel pretty good. But until that's running in JavaScript in Windows XP in a computer science lab in a 6th grade classroom, it needs to be re-engineered to the platform where it's actually going to be real time. And that's when we'll start to know for sure. I can make all the mathematical arguments I can that it's as simple as it can be. But I have a pretty good feeling on it though.
You can analyze your existing code and say, is it log n?
Yeah, and that's what I'm going to be providing is that detail through, and that's sort of why I threw the graph in. So you see, like, each one of these each step here is worst case n, and the n gets smaller with every successive column you go through. So for a particular project, it is O of n squared, where n is the number of blocks on the project. For the projects that I worked on, because they were limited activities, the block count never got very big. You basically saw every possible solution size already in this. Like, you saw all the blocks that are necessary. How this runs on the monster projects is yet to be seen, but also not strictly relevant for the goals of the tool. Yes.
We have a slightly related question from online.
Okay.
Let's make sure that.
Yeah, let's look at the committee
Well,
first.
it's related to one of the committee questions.
Well, Holly can jump in, sure. But no, that wasn't you. That's.
The code has people inferring about what's going on based on the code alone.
I'm sorry?
Coding has people inferring what's going on based on the code alone. But
Yes.
not what's going on.
So there were, okay, I know what that question is getting at. That question is getting at what do we actually know the student was doing? The only thing we have to work from are the artifacts that we presented here, where we have the playback of their blocks. We can see their project at any given moment in time. We do not know what that student was physically doing in real life while they were doing it. We don't have video cameras on the kids. We don't have sound recording. We don't have like a detailed journal log of what they were thinking at the time. So everything is inference at some level. That's the data source that we have that we can work from. it's decent, but it's not as good as the really small, high detail study where we call in one kid at a time and put a video camera on them and capture their screen. And that's a different kind of study that may be useful to get some of these more details out later. That's not what we have right now, which is a good point.
Why does it matter that it's a block-based language? I mean, the block is just a representation of an AST node, so like, couldn't you just do this on something that just uses a normal programming language?
It is, and I swear, Jay and I didn't work this out in advance. It actually doesn't matter. So the question Jay asked was, why does this have to be blocks? What does it matter? Is block not just a representation of an abstract syntax tree anyway, which you can generate any number of ways, text being one that comes to mind? And the answer is no, it doesn't have to be blocks. For the purpose of building these tools, blocks were both convenient because it gave a really easy way to know when to capture the snapshot. That was the biggest reason to use blocks from the research standpoint. Was that alone was moving a block is an easy to identify atomic operation. And even then, I still had to do filtering on it because you could still type in character by character into some blocks. There were some long moves that like came across as 2 or 3 changes that were really just one change. I still had to do filtering on it. And in the research on learning analytics, there was a lot on what is the right size byte to take of this kind of data. And character by character editing never gives you anything useful because you want to know what their thought was, not how they spelled it at every incremental way up. But getting to an AST is done in every program ever. And now with these tools developed, I do believe we can go back and we can apply them to other things. We just need a different way to define the capture point. And that is something that is different for every language. If you look at Darrell Lippman's thesis, he had to, a big part of his was defining what is the capture point when you're doing C in an online environment. It is very different, and therefore the data he got was characteristically very different. He captured on save and run. And that looks very different than this because there could be huge changes. So how do you get that atomicity of your data on text is still sort of an open question. There's work on it, and there's more work coming out every month that goes by. But that's all you have to answer. Answer that, and you can apply this to whatever language you want. If you can answer, how do you define the atomic snapshot? Yes, Lynn.
So I want to probe this a little more. So in Darrell's system and others, you're waiting for compiles and so on.
Mm-hmm.
What do systems like, black box and quiche and so on? What was the fine gradedness versus coarse gradedness of their?
So black box is use Greenfoot, the semi-visual object-oriented environment. And I know this is getting live broadcast to the internet and saved forever. So if I misspeak, I apologize. From my memory, I believe they also did GUI changes. So it was very similar to this. But there's also textual code involved, and I'm not sure how they divided that up. From what I did look at in detail, if we want to go to 2012, Peach et al. From Stanford, who instrumented their Java class, they were doing a Carol the Robot activity. They instrumented on, they basically were doing typing with timeouts, and it was okay. But they actually, what the data they actually used were their saves and runs. But that was also Java, where there's a lot of typing to get an idea out. Every language you come across, you can put that in a little place. I have a really cool paper. I'm not remembering who wrote it. It's in the lit review where they actually said, and I should put more into this on the lit review, actually. I should draw this out explicitly. Lit review, snapshot atoms of other systems. Where sometimes they go character by character and then try to deduce where the words are. Sometimes when you hit space, they would capture. I've seen all sorts of different ideas of how to do this. Everybody who's done a text language has done it either on run compile or something completely differently to them.
Isn't this only the first half of the story, when you take the snapshots? The second half is the particle analysis method, where you're comparing the student's work to the classical solution.
Yes, well, at that point, I'm operating basically on an AST search anyway. I'm working on a syntax tree. So however you get to that syntax tree, just plug that in first, is my assertion. The fact that it's blocks makes the syntax tree very easy to analyze because you're looking at it, especially in App Inventor where the blocks are function-like, they're scheme-like enough that you really are seeing the syntax tree kind of in front of you. So that is the same representation. I believe, I don't remember who this was. I don't remember who it was. I know I've read a paper where they did analysis on the syntax tree itself in abstract, where they took code, I believe it was Java, and they actually ran a linter on it and used the linter to generate a tree and then did this kind of interrogation on that tree. So you just need to add that layer. So that's for everything past the data collection. You can do the same things, you just have another layer of interface to make the tree if you don't have one already. Blocks gives you the tree, there it is. And that's nice of it, but not necessary. I think Jay beat you by a little bit.
On the topic of like generalizing a little bit, you stressed quite a bit about how the particle method is all about seeing how close you are to this known solution.
Mm-hmm.
Why is this actually a good metric and why couldn't we use another metric? For example, many classes use automated grading systems which already take a program and give a score between 0 and 100, which is a normalized score like what you're interested in.
Yes.
So how different would this be in that situation where we're seeing like how much their grade is improving? And obviously, you know, you could replace that with like any sort of, like maybe the grade that doesn't require you to have all 400 test cases that we can imagine would work.
Right, well, basically, so the question is, in generalizing this out, how is this different than a system with auto grading that has tests and is producing a score for a teacher to assess anyway? Because auto grading is one large camp sort of near the space. Another large camp is intelligent tutoring systems, which is actually a little closer to this than auto grading. The answer for that is sensitivity and granularity. That the difficulty in picking up the fine details between test cases has to do with how well you wrote the test case. And writing every single possible test case is necessary to get the full expressiveness of how close they are to the answer. I can pick up things that are more subtle, I purport, where if they have a block that's nearby, you could write a test. Basically, you could implement this in an auto-grading system. You could implement this concept where you are looking for every possible fragment, every possible particle, and somehow having a test written for that if your system can allow for that. That's basically what I wrote.
This one gives credit for pieces of an answer before they're assembled into a functional thing.
Right.
Where autograding wouldn't do that.
So the answer...
So autograding would give you totally zero because nothing works. But this might say, well, you're really close to getting it working.
Yeah.
That's the main difference. And actually, in that space in between is where intelligent tutor systems are trying to do their thing, where they are trying to do real-time data mining on what you're doing to figure out what hint you need automatically. And that is also different than this because they are, well, actually, I took a lot of that literature into account with this because they have, they try to do this fine grain. I had a thought there, I'm sorry. What were we talking about? We were talking about the intelligent tutor systems in the middle. The intelligent tutoring systems typically also aren't quite as fine-grained because they have a list of hints that they are then trying to apply to the data rather than taking the data and trying to just drag out how close are we. So it's also very close in the space, but doesn't exactly do it. And I guess if you were clever enough and had a flexible enough intelligent tutoring system, you could implement this and that. But it also gives you a different nature of the data where they don't so much care how long you've been. They don't care how close you are. They typically use machine learning to try to extract failure patterns wherever they may happen and then say, I know a hint for you. So a lot of the same engineering goes in at the beginning and then completely different questions are asked on the way out. So we're nearby and I want to be better friends with those people. And actually I found a great paper like last week by Leanne Sudol, who sort of is a big step in that direction, where from intelligent tutoring, she found a metric that was trying to say how close are we to an answer, and then built this probabilistic model, which is actually the very first thing after this dissertation that I want to take this and plug into her probabilistic model and see what we can get out of it. But that bridge is narrowing.
The reason I ask is that having to have a particular known solution is like really limits the applicability.
Oh, it's a huge constraint to
Like,
need a
in
known
a
solution.
class, having everyone supposed to turn in exactly the same thing is a really bad idea. Because it means that, like, by definition, everyone is like you can't detect plagiarism because everyone is supposed to.
Yeah.
do the exact same thing.
Yeah, Jay points out that having a known solution, a known canonical solution, is a weakness, especially at the undergraduate level, where you want diversity of thought to prove that they understand. This was targeted at the middle school level, where if everybody passes in the same thing, that's often a good thing, because they are trying to get the step off the ground is so much shorter than what we're trying to do in undergrad. In general, no, another future work that's in the paper is, or it might not be, I'm going to write to make sure I put it in. Plagiarism detection may actually be possible here, and it's something interesting because we have a potential for physical locality. One thing that I found interesting in working with these data were, can we see a particular molecule float through the room in real time? Can we see the physical patterns in which the answer spreads? And are we going to find little hotspots, little loops that tell us something? And that's interesting because this will, at the very end of the third column of the teacher tool, be mapping onto a real classroom that the teacher set up somehow. Potentially there's something there, which is interesting.
I only have one last question.
Sure.
Which is, can you use this to actually evaluate the teacher or the project? Because different projects in the same group of people have different gradients, and that kind of tells you that the project is easier or harder, or the teacher's teaching it more effectively.
So the question Jay asks is, can you use this to evaluate the teacher or the project, the assignment itself? Evaluation, use as an evaluation tool. That is not something I had thought of until I started the focus groups with the teachers, and they started saying, oh, this would be a great evaluation tool for me to give to my principal, for me to figure out which assignments have sticking points. So I believe the answer is yes. The teachers saw the potential in that before I did. So a very simple yes, that is very possible.
Those are two really different questions bundled into one, evaluating a group of kids' work over one assignment versus evaluating.
Well, either way, what makes those two questions similar is that is not real time, that is retrospective, but also in from the teacher's perspective. So the teacher, after the class is over, would then go back and look through, look at charts, look at line graphs like we drew, and see if there's a sticking point, see what's going on, and potentially grab these line graphs and we have some fit functions so you can see acceleration, and then you map those over multiple activities over time, and that starts to turn into a report of progress vectors. And either way, it's the teacher looking back retrospectively, so now they're working in post hoc data on the same tool. So adding some features to do that.
I think my main observation is that teacher self-evaluation versus external evaluation of teaching are two totally different.
Oh yeah, agreed that teacher self-evaluation, external evaluation are two different things. The mechanism to do them would be very similar, but they are very different things conceptually, and I agree. And that's why you said the two questions Jay asked were very different, though in the same sentence. All right, you had one more, I think?
Are there other, so I'm really taken with this particle analysis. Are there other domains than programming than you can imagine applying this particle analysis to?
So Lynn asks, are there other domains in addition to programming, external to programming, where this sort of particle analysis style would be applicable? And I don't know, probably. I hadn't thought about that. That's a really cool question.
It's actually programming, right? People using CAD systems are actually just programming.
Right. So that's another, I like the question because it talks back to sort of what Jay just said, that CAD systems are really just programming. A lot of people are programming and not knowing they're programming. And there's an argument that if you are, you could pull this out of the bottom of that and do this sort of analysis. If you're doing statistical models, you're really programming. If you are doing stuff in Excel, you're really programming. There's all this democratized programming that has snuck into people's lives and they don't know it. And that's kind of cheating your question by saying, are there external domains? By saying, no, they're really internal domains. But either way, I think that there may be, because the core things you need is you need a blow-by-blow recording of it, and you need the recording to represent a tree that can be compared piece by piece. Anything that can be resulted in that, you can do it. Written language is a syntax tree. Of course, saying here's the exact paragraph that is the answer is not likely to give you tractionable results. But theoretically, you could maybe get something out of that. But I think there are domains in the middle that have structured syntax that could work. All right, committee, would you like to open it up to the floor?
Please.
Okay. I'm going to start online. They've been very patient.
Okay, one thing that's actually kind of my own comment to that.
Farzine.
Has anybody used Wiley online? Like for Calc 3, I know that I did that. I had all of my homework was online. And so they could have easily done this when I had no idea how to do it.
Were any of you kids doing mastering physics? Remember that piece of, yeah. Those are all in that. So mastering physics, Zybooks, Wiley online, those are all those are all constrained known solution problem solving domains. They all count for the predicates that I set out. The data is structured differently, but I think could be processed and interpreted to work.
Farzine, are you still suggesting that those systems would be better if they did this because they would recognize pieces of a solution rather than only the whole thing?
I think that would be great, because I know that I got really frustrated with that Wiley system because it often marked this as wrong. You didn't have the right number of decimal points.
And that is a trademark of those tutoring systems. Is you would get something slightly wrong and be completely wrong. That it's 4 and you didn't write 4.0, and it's like you're completely wrong. And processes like that may be improved by analysis methods like this, where you're like, well, how close are you though, if we break it down? And especially like those Wiley online and mastering calculus and those systems, the answers often aren't single statement. They're often expressions of some kind that you have to build. And that means there's more room for you to be kind of right. And the systems continually fall on their face for getting that right.
Especially with something like Calc 3, where you have so many variables.
Yeah, especially in calc.
And you don't DYDX, you don't draw it as a delta.
There is a lot of room for interpretation, and those commercial systems still do them somewhat poorly. So maybe development as well.
But,
this is all open source, by the way, everybody. You want to grab my stuff? You can go for it, Wiley. Make the world a better place.
he just answered my question.
Oh, great. Okay, we're gonna bump it over.
By the way, I'm
okay.
sorry, I have
She has a backlog of so we'll hit that.
first, plagiarism detection was the question that you already answered.
Could do, maybe can do interesting things with physicality.
On operating on the tree itself, we're getting a suggestion that could be Peterson and Hall from the latest ICER.
Yeah, actually, I think I just found that because ICER just happened recently. You have that. I'll take those notes down. Thank you, whoever said that.
Elizabeth asked about think aloud students for validating the instrument.
Think aloud. Yeah, that's the kind of study that doing a think aloud study to validate the instrument would be a really good next step. That would be like, I take a camp, I have a closed cohort where I've done all this sort of in the n hundreds range and be able to do it again with n dozens and really look deep into what they're doing and record every facet of their interaction and be able to say, for sure, I knew what you were doing, I knew what you were thinking at the time, therefore. Yeah, and that would look a lot like what is hanging on the wall outside for the master's work, because that was an in-depth video camera study that could be done. Thank you. I know we were on a misaligned bit starting 15 minutes late, so some people got to go do things. It happens. All right, I'm going to pop out. Charles?
Okay, so how would you handle an approach to a highly economic solution? Jay mentioned somebody programming something by drawing a cat. Well, in the world of CAD, there are two very broadly different approaches to modeling a part. There's the thickened stitched surface part, where you define a part.
Oh, yeah. So in CAD, there's
there's a series of shells
Mhm.
constructed around and then individually thickened out to the thickness they need to be, versus the
You accidentally touched on his thing.
where you build individual features onto a block. Think of it like stamping something from sheet metal as opposed to milling it in a CNC. One of these is the way General Motors does it, one is the way Chrysler does it. If you were to
Whole
come up
schools of
with-
thought there. Yeah.
if you were to
So
come up- so here's the question from that.
okay.
If you were to come up with a nearly perfect, chunky, solid model of a part that the instructor drew as a thickened surface, how well would a method like this approach it?
So the question is, so we use the example of CAD as a non-programming or semi-programming domain, but the domain has many different approaches that can result in the same end object. How do you get there? I believe the end result there is that you need to have some parser, some processor that will reduce you to that tree of the final truth, however you got there. I don't know how to do that in CAD. That is a computational geometry trick for someone else to figure out. But that's what you would have to do, is you'd have to find a way to reduce it in some measurable way. And that's a whole different feature extractor thing. If you could constrain it more, you could do it. You know, everybody should be doing it. I mean, I know even different softwares think about it different ways. But the end result should have something. I mean, off the top of my head, I'm thinking of a projection mechanism that would, you know, what shadows does it cast? Is that close? Kind of thing. But you would need a layer of interpretation there to pull it off. All right, I'm going to go in here.
It seems like you give more or less all of the atoms equal weight in the solution.
I give more or less the atoms equal weight. That is correct.
So is there opportunity or potential for you to determine if students are flailing at specific sections of the problem? And would that give you the opportunity to improve the problems themselves?
Yeah, so that's a really, so what's being asked is, because could you use this to find flailing at particular points of the problem because you are looking at particular atoms of the problem? Can you detect which atoms are problematic? And right now it doesn't. It does treat them all the same. It weights them. It just counts them and moves on. But the tests, I don't have the tests in this slideshow anywhere. The tests themselves look for each atom on their own. And there's nothing stopping that from being implemented to say which one was found and which one wasn't, and how much of the score came from which atom or came from which molecule. So that would be actually an interesting avenue to go with, is identifying the parts, the troublesome parts themselves, by knowing which ones are found. That's a whole new dimension that like blows up the dimensionality of the data you get out of it. But that is very possible, I think. And that's a great idea. Were there questions, Jesse? I'll get you, Darren. I'll get you. Okay. Graph that's on here right now. Mm-hmm.
Go back to the previous slide.
Maybe that'll work. There we go.
No, not that. Sorry, the one with the flow chart.
Oh, the one with the flow chart. Oh, that's not what I wanted.
Anyway, all I see are plus ones. I never see minus. So I'm a little confused as to
Oh, okay. How do you get back down? So that score, that flow chart I showed you, I know what you're talking about now. It counts from the bottom up each time. So you were thinking of this. Score is 1 when you find one. Every time you make a change, it starts back at 0. That's how that happens. That's good. Right. Well, that was a great detail, that the score does not persist over time. It is recalculated. There. You've been very patient. Thank you.
Building off of what Jay was talking about with the problem of the known canonical solution, would you run into issues if, say, they have the right solution, but they added a little something extra in there, like maybe they had to print some extra string they weren't supposed to print, but they still technically got the correct solution to the main problem?
So the question is, how does it handle if they're adding extra on top of the problem? As implemented now, it would largely be ignored. that it finds what it's looking for and happily says, I found it, and that's the end of that. It is not doing auto grading style testing, also like Jay said earlier, where it's checking the output. It's not actually running the app. It's not actually running any of this code. This is linter style. It's looking at the code, but it's not.
Score really well with a non-functional program.
You can score well with a non-functional program.
And so,
I think at 100%.
Not well. Funny you should mention that. There is a particular bug in my implementation that I found where it is possible to have broken code that scores higher than the proper functional code, giving you a higher than maximal score in a very particular edge case that overrepresents. The algorithm as is right now occasionally overestimates if you trick it.
I suppose you can also say, like, if false, then the correct solution. So then when you run it,
it looks like it's there, but we'll never hit it.
Yeah.
It would happily award that. Unless you specifically, I mean, depending on what, it's based on what the parent of every atom is. So if the parent of this thing is supposed to be top level and you stick it in something else, then its parent is wrong. So maybe not. There's some nuance in there, but I think the answer is largely yes, maybe, hopefully not. It has been known to overestimate here and there, but the overestimation has not been the order of magnitude of the graph itself. You can still see when they're, because the answer that exercised that bug was really close to right. Really close, but doesn't work.
and I'm sorry, on the other side of that, if, for example, I saw in some of your examples or your projects, you had specific strings that you wanted to output. And if they changed that somehow, whether they didn't have the exact punctuation or capitalization, would there be any reduction in points if they didn't have the exact
So
string?
Darren's asking about exact string matching. I actually do have a distance to correct string already built in. So I tell it the string I want it to do, and I give it a how many. If I hadn't just talked for an hour, I'd remember this word. It is, yep, it's a Levenstein distance. And actually, I specified for each string that's in these answers how much of a Levenstein distance is acceptable, which is actually an easy HMM away from auto detecting by itself. That's very doable. That's very doable. That was an easy one. That was an easy one. All right, let's go. Let's start with yes.
All right, so you touched on this a little bit, but I was curious about the fact that anytime that you add a rubric into an educational system, you run the risk of people trying to maximize the points instead of doing the actual thing that you want them to do, like getting them to learn, or if you're a student, making it so that my graph looks like it, so the teacher doesn't come bother me to either help somebody else or tell me that I'm not paying attention or whatever. In this system, is there anything, this might be more towards future work with the dashboard or not, but is there anything in the system that would make it more or less robust against that type of gaming and scoring?
How do you get around gaming the system is the question. I also just switched the Omni mic, so hopefully everybody at home can still hear me. So maybe you can catch what they're saying as well as me. So how do you prevent gaming this system? There is a canonical, so answer one is in general, the students aren't confronted with this. With an auto grading system, you are explicitly interacting with your assessment mechanism. In an auto grading system, you give it to it and it goes 50, and you go, let me try again. Here, the model that I built this under is the student doesn't really see this. I did have one teacher say that they would like to use this on the projector so they can move around in the room. And that's when they said, no, don't put their real name on it. Let me put a code name or a student ID or something. So students can't necessarily easily encode who's who. So they can't look at each other and be like, oh, they're ahead of me. I think that is fraught with issues that need addressing before that can be used. But that particular teacher thought it would work well for them. In general, this was not intended for the student to see, but that teacher also at another point in our conversation said, no, I want them to see it. I want them to know what I know. That was the teacher who also first brought up the needy students who would ask for help without ever trying. So it'd be like, I need help. No, you don't. I mean, you might. We don't know yet. That teacher was adamant that this being public would not be a bad thing. I'm unsure. I don't
Some
know.
will turn into a version of Clippy.
Yeah, don't let it turn into Clippy and just being an annoying thing saying you're not near this arbitrary goal that Mark said you should be near. That would be a bad one. That's why having it be public is a strange question that I did not intend to be possible. Yes.
So I understand your presentation was focused on middle school children that were working on things like, the simple debugging activity or the temperature activity, but depending on the complexity of the kind of assignment that you'd be monitoring this on, rather than like a single canonical solution for like, because I understand that's a big constraint that you mentioned, but what if there's a way to detect canonical solution chunks? So like if there's a big application, let's say, and a student has one part of it working and they're close to having another part work, but there might be some small thing like a segmentation fault where if they remove that segmentation fault, boom, like it starts to like, all click into place. So like,
that's actually really close to the bug I was talking about earlier.
Because basically like, you could have canonical solution chunks where like maybe their entire solution might not be correct, but they have like, several parts that you can identify as like, yeah, all this looks really good, but there's like, these one or two parts that you're stuck on.
So I would wager to say the scenario that you presented, where basically you're talking about bigger programs.
Right.
This would handle that perfectly well in its current form. If you have those canonical chunks, that's the whole point of the molecules, is you can have a bunch of different molecules buzzing around each other unrelated that still count.
Okay.
So you can just build a bunch more molecules that do different things. Maybe you have one, maybe you have another, maybe some you're close, maybe some you're far away. All of that can be scored together. And if we combine that with Nick's know which chunk is being problematic, then we can start to get some really cool insights into how that student is actually doing. But I think what you proposed actually will just work as is right now. I think it'll handle it fine.
Okay, because like, a good example is, I understand you were going off of the MIT app.
Well, I gave you very trivial examples. These are very simple activities. It has yet to be seen how well it will work when you toss against bigger stuff, but the concept of it, which is not a graph anymore, the concept of doing the particle tests should scale. It does in theory, and should be able to handle what you do just by writing bigger solutions and then seeing how close you are to them.
Okay, because the variation among solutions is very interesting. So if like that particle, like molecule idea will still scale to like larger applications.
Well, if you know sort of where you want them to end up, you could end up with nobody ever getting this high. Where you say this would be perfect, absolutely everything running, and this is an operating system. And an operating system should score 10,000 points on this, and people are flopping around 60. That could be good. And everybody got to that 60 a different way. How to then use that in the pedagogy, that's a whole different question.
Okay.
Let's take one more.
Yeah, one more from the
Three
audience.
more hands. Three questions.
Thank you, Fred. Michelle.
I'll be quick. You talk about the students who succeed in flailing.
Yes.
How long is flailing a problem, and is there a point of no return where they can no longer succeed after flailing for X amount of time?
So that is actually a cool thing that I could interrogate the data to find out for sure out of my collected data. Now that we have a windowed way of saying this is flailing algorithmically, we could say, all right, this person flailed for this percentage of the time and then didn't, or then did. We can mark it as flailing, we can mark it as progress. I don't know what that would look like in our data. There's no reason to suspect that there's a point of no return intrinsically, but that's a next level analytic that would then be actually really cool to inform the teaching, because you could say, well, if students haven't gotten it by here, they're not going to. And that becomes a heuristic that can then turn back out. And I think that is one interrogation away from this data. For it to be meaningful, I'd need a lot more data to run it on, but I think the idea is very sound. Yes.
More commentary than anything. I'm a nursing educator, and we do have students who flail even with the medical math, acid base, things, concepts like that that are difficult. And having this type of a program for the teacher would be able to identify the flailing right away, like you said, as opposed to your test, final test 0 to 100. And that way too, when I saw the red and the blue graph, is you have some students who immediately start moving right up and others that are going for a long time. And I know on the high school level, oftentimes they'll pair students together, and that would give you an option, an open door to which students I should pair with another student, so that they could maybe work together. And then it also is good, as this gentleman over here was saying about, as the teacher can kind of take a look at their assignment and see, gee, I have two, it looks like I have two different levels of a class right there.
Yeah, if
You
you
know,
look
maybe
back
I
and you
need to have a little
see,
pre-req.
you start seeing this
like a
in your
pre-test.
assignments in the pre-data,
Yes.
that starts becoming very useful
Right.
as an assessment point for
curriculum.
yourself.
Yeah,
That if
and
you-
then I think overall the dashboard's a very good formative assessment as opposed to summative assessment of how a teacher and student is doing in that course.
Those are words I
And
should be
that's just what I'm
saying.
saying. Good job, Maki. It's the mama.
All right, who else had hands up?
So this has been touched upon before, but with molecular analysis, you analyze whether the structures themselves are close to the answer. Is it also possible and would be effective to at the same time test functionality is close to the answer? So with like a test case, which isn't quite at the end of a program running, just the auto grading, but as it's built to test whether or not it's actually functioning and possibly reward that difference.
So what you're asking is adding functionality testing on top of code analysis. So that's rolling in not just an autograder, but an autograder that is rolling with you every change you make, which is sort of what IDEs do, right? You're using any modern IDE, it's compiling basically every step of the way, whether it works or not. And that's actually where a lot of this research started not long ago, actually over a span of between 6 and 15 years ago, is why don't we just compile it all the time and see what we get? I think that would become a more powerful tool that could be better for being student-facing. Again, this is not a student-facing tool as intended, but that gives the teacher, so the teacher could say, here's where they were, how close they were to the code looking right, and here's where it started to work. The problem with doing the started to work is they tend to be very modal. It entirely doesn't work and then it entirely starts working. So it would have to be laid on top. And there might even be a visual way to do that on the console itself. I got lots of different suggestions for visual add-ons to this talking to the teachers. But that's an interesting one, is not just stealing from the research of auto assessment, but actually putting one in. All right, was there one? I thought there were 3. Was there any more?
Thanks
At all? Thank you very much.
Thanks so much.
All right, so everybody on the live stream, I'm going to sign off. Thank you for joining us. See you all soon.